Good morning to all our dear viewers. You are welcome to Homeschool Program, our daily program that runs from Monday to Friday, facilitating our learners who are at home. We are so grateful for the wonderful opportunity Pastor Jackson Senyonga and Pastor Eve Senyonga they have tried to give to our students who are at home. They are sponsoring this program. They are wishing the best, all the best for our learners who are at home. So it is a really a very good offer. We have to keep appreciating them every day. Okay, where need be, we need to celebrate them. Okay, so Kodai School, the school which is assisting in delivering content under the management of Madam Chemelilo Lydia. We are also grateful for your great work at Kodai School. We are going to be handling Thermo Chemistry. Saul Abooki, a Facebook page if you want to contact me, Saul Abooki. YouTube, all these videos are copied to my YouTube account. You can visit it and get all these videos of the lessons plus other lessons. Twitter, I use that Saul Abooki, or you can contact me on my telephone number, which is right there. So I've always told you that it's always good when you wake up. It is a habit that we should teach to one another, that you make sure you greet people in the house, people you are working with. Even if you sleep with someone in the same house, in the same bed, you need to wake up and greet them. You never know how they are. Okay, so I want to take this time to send my special greetings to all staff of Kodai School, CLC, all students of Kodai School, my people from Toro region, comrades in the struggle. I want to repeat that one. Comrades in the struggle, fellow countrymen and countrywomen. People always ask the struggle. Even this one is a struggle. Okay, we are in the struggle to make sure that our country gets the best education. Okay, we are in the struggle to make sure that our learners succeed in what they want. Okay, so whatever we are doing there, it is a struggle. So in any struggle you're involved in, please make sure you work hard and remain committed. So I've told you that we are here and a number of things should be done. So for you there, get a notebook, get a pen, get a pencil, get a calculator, whatever is required, put them next to you. So that whatever we are going to be covering, you are not moving, you are going off the TV, looking for a pencil now, looking for a calculator now, and always I've told you, be with a functional calculator. Invite a brother, invite a friend, invite a sister. Don't attend the lesson alone. I've told you it is a good habit to greet. It is a good habit to wish for others. Okay? Don't stand and say, let me sit and study. I will explain to them. No, sit and study with them. You can as well go ahead and explain to them or discuss with them. Don't compete, just work together. Okay, on our website www.kodaischool.ac.ug, visit that website. All the content that you need is there. And for us, we don't limit that you should only be a student of Kodai School. You can be a student elsewhere. Visit the website. You never know. You might like it, the content which is there. You might say that, no, I'm tired of visiting the website. When the term resumes, I'm going to Kodai School to be next to the source. Okay? It is also, we welcome you. They say that the gate is open for you. Come and study immediately when we get rid of this pandemic. You can visit the top television page for the videos. They always do the live stream. they don't live stream, videos are always uploaded there. So it may come on time or it may come late, but visit and get the videos. Okay? They are always there, or we are always live on top television page. If you don't have a TV, you can buy few data and you do what? You'll be able to watch or to study with us. Also, we have Kodai School Seta Bajo FB page. Like it so that you can keep receiving the information. We communicate using it, whatever we have. Okay? Right now, we want to go to our topic, which is here right on the blackboard, Thermo Chemistry. We started this topic on Monday, and we said that when we start it, we give it an introduction. We gave it an introduction, and we said with every day we are going to be looking at a different segment. So today we are going to measure in that segment, which is called enthalpy of displacement. As I've always told you that enthalpy can be heat. So we can say heat of displacement. Today, what are we likely to achieve? I want you to achieve two major things. At least if you can achieve them with me, then it will be so nice. And I know by the grace of the Lord, we are all going to achieve. By the end of this lesson, I want you to be able to describe an experiment to determine the enthalpy of displacement. When I say describing an experiment, it means that you give an aim, you give the materials, you give an illustration, you give the procedures that are followed, you show the results that can be attained, you treat the results, you give an example, and you calculate it. So all those things will be put into that objective, and we shall achieve them. Describe the heat changes during physical processes. Also, at the end, we shall look at these heat changes during the physical processes. Okay? We looked at that slide. If you can go to the next slide, we can see all these types of heat changes that we have been looking at. We have seen the enthalpy of combustion. We have seen heat of solution. We have seen enthalpy of neutralization. On our next slide, we have seen enthalpy of displacement. We have seen heat of formation. And then we also talked about heat changes during physical processes. And those ones we said melting, freezing, vaporization, combustion, condensation, and many other processes that you know they are termed to be physical processes. Okay, so we have been explaining one by one. So today, allow me take you through enthalpy of displacement. Okay, enthalpy of displacement. We can see that so many atoms, so many elements that are not reactive, that are more reactive, displaces those ones that are less reactive. Okay, so that one we studied it in senior 2, senior 1 chemistry, depending on how your school handles the content. Okay, some schools teach it in senior 1, others in senior 2. You studied about electrochemical cells, electrochemical series. Okay, electrochemical series, you saw that elements, the reactivity of elements, where you begin with the potassium as the most reactive, you go to sodium, you go to calcium, you go to magnesium, you go to aluminium, you go to carbon, okay, and so on, up to the last element. If you visit now my senior 2 students, they will tell you the formula, or the students that I teach. Everyone, I think it is a song, you know all those elements up to down, copper, mercury, silver, and gold. You know all those ones. So here we are saying that elements that are more reactive, they displace those ones that are less reactive. Okay? Look. If people would use a formula, we shall find that you have potassium, sodium, calcium, aluminium, hydrogen, zinc, iron, tin, lead. Here we have carbon, not hydrogen. Here we have hydrogen, copper, mercury, silver, and gold. Okay, we have all those ones from potassium, sodium, calcium, magnesium, aluminium, carbon, in bracket, zinc, iron, tin, lead, hydrogen, copper, mercury, silver, and gold. So we are saying what we are giving there as a statement that are the ones which are more reactive. So the reactivity decreases going down, okay? So it increases, that is the increasing reactivity. This side we are seeing the decreasing reactivity. So we are saying that those ones which are more reactive, they tend to displace these ones which are less reactive, as we shall be seeing in one of the equation there. Okay? So what do they mean by displacement? They are saying that if you are weak and a strong person comes, you will be displaced from the place where you are. Okay? Even if this one we can see it in power. People who contest, we say that if this man is strong, that woman is very strong, is going to displace the other one from the seat of MP. That means if you are contesting on the seat for MP, okay, there is someone who has been there, is also coming back, and for you, you are just fresh. So for you to be able to displace that person who is there, you should be stronger than the person who is there. If you are weak, that means you are not going to be able to displace that person who is occupying that seat. Okay, so that one also is here applicable in chemistry, that if, for example, if an element here forms a compound, is having a radical within a compound, and another element come, so here we are going to pick an element like copper. We have copper is in a compound with a sulfate radical. Okay? We are saying we have that one. Okay? We have copper 2 sulfate solution. So we want to bring an element that will displace copper. Remember, copper is having a sulfate. So for this sulfate to be taken away, that element, if we can look here that copper is here. Are you seeing where copper is? So which element can displace copper? Very well. That means that element should be above copper. We have said that for someone to be able to displace you from the seat, from the area where you are, it should be stronger than you, should be more reactive. Okay? The community should receive that person, should be responding to that person more than they do on your side, okay? For that person to be able to displace you. So here, the one which is more reactive will be able to displace the one which is less reactive. So it is evidenced here, we say that copper, if we react it with zinc solid, we shall be able to say that copper will remain alone. They will remove the zinc, the sulfate, and the zinc will take the sulfate. Okay? Reason, it is given here. We are saying that the ones which are more reactive will displace these ones which are less reactive. And you can see that zinc is here, copper is there. So for a student who is there, will ask, what about when you get copper 2 sulfate aqueous? You react it with, for example, silver. solid. Okay, what is the answer? So here, whenever you get these equations, first look at the reactivity theory. Is it favoring the displacement of copper? Okay, is it favoring the displacement of copper? If it is not, you just say no reaction. So if they are asking for the observable changes, no observable change, because there is no reaction that takes place. Okay, that's it. That one I think is understood. You follow the reactivity theory. For the students who work with me, maybe I will upload it there, the formula. Okay, it is good. You know, can be hard for you. But when you see here, you find that Capella serves canned meat as Zaytun invites Tina and Lady Hajar. Okay, or Hannah. Company manager said goodbye. So we use a formula to understand this one. Okay? We use a formula to understand this one, to be able to put these elements in their order, decreasing order or increasing order, right? So we just brought this one to make sure we emphasize the point of enthalpy of displacement or displacement. How does the displacement take place here? How is it possible? It is very possible following this trend, that if an element is higher than the one which is in the compound, that element will displace this one and it takes over the compound, right? I think it is okay. So that slide was showing the example, and the example we have already explained it. We may not go back. So we are going to go straight to the experiment. Okay, we have an experiment to determine the heat of displacement of reaction between copper 2 sulfate solution and zinc. Having seen this equation taking place or being possible, so we want to see how can we carry out a practical experiment in the lab. Right? Very soon we shall be going directly into the lab. Just keep watching every day, every week, don't miss. Okay, so we are saying now we want to look at the experiment. Remember, it is one of our objectives. We are saying this experiment we are going to say to determine the heat of displacement of reaction between copper 2 sulfate solution and zinc. Right? So the procedure is very clear. Hopefully that all students know what it means by plastic beaker. Put a known volume of copper 2 sulfate solution, and you call that volume V1. I don't know, maybe it will be 50, it will be 40. So don't copy from the neighbor. The neighbor has used 40, you want also to use 40. The procedure is clear, a known volume. If you use 30, stand with your 30. Don't just change because the neighbor is having a different volume. Your volume will give you the correct answer. Okay? Put a known volume of copper 2 sulfate solution and you call it V1. Of known concentration, may say M1. You never know, it will be 2 molar, 1 molar. Sometimes those things are written on the bottles supplied in the practical room. You find there 2 molar hydrochloric acid. Okay? 2 molar copper 2 sulfate. So that is the concentration, right? Pick it and be able to use it. Then after putting copper 2 sulfate alone in a plastic beaker, you just need to stir and record the temperature, and you call that temperature as T1. Okay? T1, right? So after that one, you add a known mass of zinc powder to the copper 2 sulfate solution. Remember, it's nothing you did. You just added copper 2 sulfate. You didn't heat that. You did what? You just added, you had to mix around, and you recorded the temperature. So you didn't change the volume, the volume, you didn't change the state, you didn't change anything of the solution. So you just add zinc powder. After adding, you stir the mixture. You mix it very well, and then you record the maximum temperature of the mixture. Okay? Having recorded the maximum temperature of the mixture, you call it T2. Right? I've always told you that once you do the experiment, you should go ahead and be able to treat the results. You put what they call treatment of the results. You put your results. You summarize whatever you have talked about in the experiment. Okay? So on our next slide, you can see that we are going to the treatment of the results. Okay? I take that one to your side, that make sure you be able to draw the diagram. Diagram is simple. You just draw a plastic beaker and you do it. Because we have been drawing these plastic beakers, so it is not new. When assuming that if you are in senior 3, you are in senior 4, you are in senior 2, you have seen a plastic beaker, because it is a very first lesson in senior 1, one of the first lessons, okay, to show you the apparatus. Okay, treatment. We say value of copper 2 sulfate solution. We have already said that one is V1. Also look at the concentration of copper 2 sulfate solution. The concentration, we also saw it as M1. And we emphasize that on the bottles supplied in the practical room before you come with your solution in the test tube or in the beaker to pick the sample. Okay? The copper 2 sulfate solution they are given generally. Please make sure you read on the bottle the concentration of that copper 2 sulfate. Initial temperature, we said is T1, we recorded it. Final temperature, we said is T2. Then we said temperature change is T2 minus T1. Remember the formula which we are going to use. We are going to look at heat change. Heat change. On the next slide, we are going to look at heat change. Heat change. We have been seeing this one. We have been singing this one. That heat change equals mass of solution. Okay? On our next slide, heat change equals mass of solution multiplied by the specific heat capacity times temperature change. That one is very important. Heat change, I want to repeat it, mass of solution multiplied by specific heat capacity of the solution multiplied by temperature change. And how do we get the mass of the solution? We say that in case you are not given mass of the solution, you'll be given the volume, you'll be given the density of the solution. And as usual, I've always emphasized that you say density equals mass over volume. So when this one multiplies here, you get mass equaling to density times the volume. That sign stands for density. Okay? So use this one to get the mass. That's why in our slide we are seeing there is mass of the solution equaling to V1 times the density of solution. It comes from that one, alright? Then if in most cases we have seen that we can assume the density, if we assume the density equals 1, okay? If we assume that density equals 1, that means we shall get 1 times V1, we shall finally get V1 grams, okay? The volume will turn to be the mass because density is already 1. Simple mathematics. Then after getting, you have got the mass of the solution, you have the temperature change as T2 minus T1. You have the specific heat capacity of the solution. Specific heat capacity will be given within the question. If we don't find it in the question, but in mind, you know that specific heat capacity should be used in this question. Go to the first page, very first page, and see all those standards which are given. Most of the standards are always given on the first page. So first read, when you're reading instructions, read those standards, or go to the last page and read those standards, where you find even the periodic table, right? Wherever they are, look for them. So in mind, be with something like a calculation that involves the standard should be given within the question, or will be given on the first page, on the front page, right? So with there, V1, having got V1 times specific heat capacity times temperature change, which is T2 minus T1. Whenever we do that, we involve a bracket, okay? So that we'll be able to use our body mass very well according to mathematics. So we are saying that will be the heat change, but as well we need to look for the moles of copper 2 sulfate that reacted. How do we get the moles of copper 2 sulfate that reacted? Yesterday we looked at that one very well. We said that moles, once you are given the concentration and now you are asked to calculate for moles, right? You are given the, okay? So you are given concentration. So if concentration is M1, right? That is the concentration they have given you. And they have given you volume, okay? V1. What do? You start with 1,000 centimeter cubed, okay, of, what do you want? You want that one of copper 2 sulfate. Of copper 2 sulfate solution, okay, yes, contains M1, right? Contains M1. Then what about 1 cubic centimeter of copper 2 sulfate aqueous contains, that means it will be M1 divided by 1,000, and those ones will be our moles, okay? Will be our moles. Then we go to our volume, which is V1 cubic centimeter of copper 2 sulfate aqueous contains M1 over 1,000 times V1. That's where you are seeing M1 times V1 over 1,000. And we are saying that those are number of moles. It's very simple. Once you keep practicing these things, you're going to find that you can pass through so many things. Just you reflect on what you did somewhere, because this one I've done it before. Not once, not twice. Okay? So a student, a good student who is willing to learn, you should not be too bright to understand these things. It is all about the heart you have. If you really feel that you want to learn this chemistry, it can be understood. Okay? So that one we have finished it. If we move to our next slide, we are going to see how well you can deal with the results. How well you can deal with the results. Having summarized whatever you need to use, how can you go further with the results? Remember, the equation should be kept in mind. Okay? That equation is very important. You should be able to write it and be able to use it. So we are saying that the moles of zinc that reacted, we have got them as M1 times V1 over 1,000. So those moles of zinc, they are the ones which evolve the other heat change. You have got V1 times specific heat capacity times temperature change. Okay? Those are the moles which evolve that heat change. Okay? So 1 mole of zinc evolves what? That means if M1 V1, okay, divided by 1,000, okay, evolve what? Evolve mass, which is V1, times specific heat capacity times the temperature change. If they evolve that one, what about 1? 1 will be this one, V1 times the specific heat capacity times the temperature change divided by this one. Now the mathematics you need to involve is how you cannot, when you divide by this one here and you divide by this one, after dividing you realize that there are two and you need to combine, you multiply, you finally get times 1000 divided by M1 V1. I've said all that simple mathematics that we have been going through. I don't want to repeat it. Just look at the videos, visit the website, visit the Facebook page, look at all the content that we have been posting on all those platforms. You'll be able to do a self-study. Alright? So finally, when we go back to our slide, we are saying that what we get there is the heat of displacement. Is the heat of displacement. Is the heat of displacement. So allow me take you to example 1. Having got that heat of displacement, we are going to write straight to example 1. When 6.5 grams of zinc powder were added to 250 cubic centimeter of 0.5 molar copper 2 sulfate solution in a plastic cup. Okay, last time we used a plastic beaker, but that is, you can improvise. Use a plastic cup. 5.46 kilojoules of heat was liberated. Why was a plastic cup used and not a metallic cup? Should we go to physics or we remain in chemistry? Why was a plastic cup used and not a metallic cup? Now part B is saying, write the ionic equation for the reaction between zinc powder and copper 2 sulfate solution. Okay? So write the ionic equation for the reaction. I want to first answer those questions as you are copying them. I want to first hint about them before we move to the next part of the same question. We are saying that why do you think that a plastic cup was used, not a metallic cup? Okay, so we can say that the plastic cup, remember, here we need to minimize the heat loss. Okay, we need to minimize the heat loss and the heat gain. If we keep having varying heat gain, heat loss from the surrounding, the experiment is going to be affected. Okay, the values will be affected that we are going to get. So the purpose of using a plastic cup is to minimize the heat loss and heat gain from the to and from the surrounding. That means we minimize heat loss to the surrounding and the heat gain from the surrounding. Right? I think that one is clear. So part B is saying you write the ionic equation. Write the ionic equation. Remember, we talked about how to write an ionic equation in our yesterday's lesson and the other day as we looked at ionic equations. Right? So we have said our equation is going to be, you are reacting zinc solid, which is the zinc powder. You are reacting it with copper 2 sulfate aqueous. Right? We are reacting this one with that to produce zinc sulfate aqueous plus copper solid. Copper is being displaced. That one we have discussed it, that has no authority of remaining in the office when a powerful man has come, or a powerful woman who is zinc has come and copper is occupying the office. They will be displaced and the strong person take over. Right? So it is natural for all those things to happen. So we put this one where there is aqueous, that means ions are existing freely. So we separate those ions. Solid plus copper ions, aqueous, plus the sulfate ions, which is 2 negative, aqueous. We get zinc ions, aqueous, plus the sulfate ions, aqueous, plus the copper solid. Right? So we say that, you see here, when copper crosses the other side, it will not do anything. When the sulfate crosses the other side as a negative, it will cancel out. So when we have this one and that one, we cancel them out. You can see how I'm cancelling neatly, not just doing this. Okay? No. Don't write and do this and start doing this. You are cancelling. No, just cancel once. If possible, use a ruler. So what remains? Zinc solid plus copper, 2 ions, that is aqueous. We are getting zinc ions, aqueous, plus copper solid. That one will be our ionic equation. Well and clear? Hopefully we are together. So let us move back to our question. Please take note of this one. It is that. Take note in a second so that you can be able to move to our next part. Right? Those ones who are responding to us, I'm really grateful. Some are raising complaints that teacher, you don't give us time to copy all the work. Sorry. We have always told you that here we are here to explain to you the content. So the copying of more so the notes, you visit the website and get the slides. You take your time, you copy very well, put them in the design you want. I know some students design their work, okay? Put them in the design you want after understanding. So we are here to understand, not just to copy things down. Then we say accountability, we wrote the notes, okay? Accountability should be here, not in the book, right? So we go back to that question, part B. Part B we are going to see, now we are going to the part of calculation, the next part, okay? The next slide we are seeing, we have part C, which is having the calculation side, right? We are seeing that calculate, okay? Calculate on our next slide, calculate the number of moles of zinc, calculate the number of moles of zinc powder. Then Roman 2, calculate the number of moles of calculate the number of moles of zinc that reacted with copper. On our next slide, the number of moles of zinc in 6, that one. The number of moles of zinc in 6.5 grams of zinc powder. The number of moles of zinc that reacted with copper 2 sulfate solution. Okay? Then also we have to look at the heat energy produced when 1 mole of zinc reacts with 1 mole of copper 2 sulfate. Then we are saying that that will be enthalpy of displacement, given copper is that one. So that is the question we always I've always told you that you take a screenshot of the question so that you can continue with the work. All right, we are not going, some people write slowly. I've told you some people want to design their work. So we shall not be having time for designing the work. So we shall just be aiming at understanding. So when we move to our next slide, we are going to see how we can calculate for the number of moles in 6.5 grams of copper. Right? Now part A we have finished it, that was the answer. Part B you have finished it, and part B you have seen how to derive that very answer. Right? Part C Roman 1 we are calculating for number of moles in 6.5 grams of copper. We looked at this one when we are covering mole concept. Remember, we started with mole concept. We took 2 weeks in it and we completed it. So visit the videos, visit the slides, you'll be able to get all this content. But for the sake of those who want to understand this question, they will say, no, let us do the question, let us do it. So we are going to begin with the standard. You know that 1 mole, I told you that the relative atomic mass is equal to 1 mole. So there the relative atomic mass of copper, as you can check from the periodic table, is 65 grams of, you get 65 grams of copper. You say they are is contained in 1 mole. What about 1 gram? That means 1 gram will be 1 out of 65 moles. Having got what is in 1, then you got what is in 6.5 grams of copper. We shall say, now we say 1 times 6.5 times the 65. We get 0.125 moles of copper sulfate. When you're doing this question, don't use the slides. Pick the question, calculate. When the answer comes out, you give a high five to someone next to you. So then when you go to part 2, Roman 2 is saying we want to calculate for number of moles in, let us go to the next slide. Yes, that one. We are going to be calculating for number of moles. Said number of moles of zinc that reacted with copper 2 sulfate. And that's what we are going to look at there. So how do we get the number of moles of zinc? We have to first begin with the known to unknown. We understand that we were given 0.5 molar copper 2 sulfate. So we start with that one. Remember, we have the volume for copper 2 sulfate. So we start with 1000 contains 0.5 moles. What about 1 centimeter cube? Will be 0.5, you divide by 1000. That's simple mathematics. I don't do it again because that's what you have been doing. I just need you to follow, and when in your free time, calculate these things. What about 250? 250 will contain 0.5 times z, 250 divided by 1000 moles of copper 2 sulfate. Then you get the answer as 0.125 moles of copper 2 sulfate. This answer looks like the answer you have just got previously, but it's not the same. For you, follow your calculation, what you get, because any answer that you get, it might be existing somewhere else. So what you need for the right procedures. So when we get the moles, once we have the moles of copper 2 sulfate, then it is very easy for us to get the moles of zinc. We say if we use the equation. On our equation, you can see that it is 1 mole of zinc reacting with 1 mole of copper 2 sulfate. 1 mole of zinc reacting with 1 mole of copper 2 sulfate to get 1 mole of zinc sulfate plus 1 mole of copper. Alright? So from the equation, we can say that now 1 mole of copper 2 sulfate reacts with 1 mole of zinc. What about 0.125 moles will also react with 1 times that, 0.125 divided by 1. That means if 1 reacts with 1, that means 0.125 will react with 0.125. Practically possible. On our next slide, we are going to look at the last question, which was saying you calculate for the heat of displacement. Heat energy produced when 1 mole of zinc reacts with 1 mole of copper to sulfate, which we code as enthalpy of displacement. Alright, that's what we are going to calculate for. Then what do? We say 0.125 moles of zinc evolve dirty energy, that which was given in the question. Okay, so we say what about 1 mole? Remember we said that the answer should be in kilojoule per mole. That means you have to convert 1 mole. So 1 mole of zinc will contain 5.46 divided by 0.125. Remember I said be with a functional calculator. Be with a functional calculator for you to be able to go through all this work very well without meeting any complication. So allow me take you to what they call heat change. On our next slide, we are going to see, or we can see, heat changes during physical processes. Heat changes during physical processes. These ones we are going to move as fast as possible. Reason? Because they are not new in our faces. Melting, a primary pupil can talk about melting. Alright? A child who has not yet gone to school may also talk about melting if at home people discuss content or use content, apply it at home in their day-to-day life. So melting, we can see that for the particles in a solid, we see them to be closely packed to each other. Okay? You know that solid particles, you get any solid next to you there. Can you see any distance between the particles? Can you observe any distancing there? There what we call social distancing, or 4 meters. It is not there. Even a meter which is there, it may be negligible. Okay? The distance which is there. So we are saying that the particles are closely packed to each other and do not move from one place to another. So what happens is that when a solid is heated, the particles gain more kinetic energy. Remember we said kinetic energy is the energy possessed by a particle in motion and vibrate more vigorously. Eventually, they are able to leave their positions in the structure and move past one another. Okay? Once a solid is heated, they are able to leave their positions in the structure and move past one another. So here on the street, we say that people can easily move when they see LDU. But solid particles can easily move when heated. Right? At this point, we say that they flow as a liquid and the melting point of the solid is reached. Right? As simple as that one. So we are saying on the next slide that we take note that the heat supplied to melt the solid causes negligible rise in temperature. The rise in temperature is not so significant. So we call it latent heat, or literally meaning hidden rise, hidden heat. Okay, hidden rise in temperature. You may not observe that even there is a temperature change. Right? So also we say the reason is that the heat supplied at first simply weakens the strong intermolecular forces of attraction, holding the particles together. Melting is an endothermic process because it involves the absorption of heat. Once you apply heat, that means that process is involving the absorption of heat. So when we move to our next slide, we are going to define a few terms that are used. We look at enthalpy of melting. You can call it enthalpy of fusion of a substance. Okay? On our next slide. enthalpy of melting or enthalpy of solution, enthalpy of fusion of a substance. We are saying that one is the enthalpy change when 1 mole of a substance changes from solid to state when melting takes place. We say that is the enthalpy of melting. Then enthalpy of freezing of a substance is the enthalpy change per mole when the substance changes from liquid to solid state. From liquid to solid state is enthalpy of freezing. From solid to liquid state is enthalpy of melting. They go hand in hand with melting, solid to liquid. So enthalpy of melting. Freezing, liquid to solid. So that is enthalpy of freezing. So those are a few things, and we said that these changes do not take place under standard conditions. And enthalpy changes of freezing and melting, we are going to see that are quoted at 1 atmosphere, and at the temperature with which the change of state takes place. So we are going to see that the enthalpy of freezing is the negative of the enthalpy of melting. On our next slide, you're going to see that this one is the reverse of the other one. Alright? Enthalpy of freezing is the reverse of the enthalpy of melting. It is practically, you have seen it and you have interacted with it. That freezing is the opposite of melting, if you can go back to primary. Okay? So here we are saying that is the reverse, is the negative of the enthalpy of melting. Okay? As we can compare the processes. So let us look at vaporization very fast. On our next slide. On our next slide, you can look at vaporization. I said these things, you don't need to drill much on them. We have been interacting with them. We are saying that, on our next slide, we are saying that the particles in a liquid are in motion. For the particles in a liquid are in motion. Okay? So, what do we see? We say that once they are in motion, the forces of attraction on the slide has been vaporization. Okay, we are saying that vaporization, the particles in a liquid are in motion, and the forces of attraction keep them in the liquid phase. When a liquid is heated, the average kinetic energy of the molecule increases, and some molecules with energy above average are able to break away from the attraction of other molecules. And also we are saying that vaporization is endothermic, because it also requires temperature, which requires absorption of heat. On our next slide, we can now just simplify the term enthalpy of vaporization. Okay? On our next slide, you can see enthalpy of vaporization is the enthalpy change that takes place when 1 mole of a substance changes state from liquid to vapor. The enthalpy of vaporization, you give us the next slide, is the enthalpy change that takes place when 1 mole of a substance changes state from liquid to vapor. So the opposite of vaporization is condensation. Alright? That is the reverse. So when we move to our next slide, that is the last slide, we are going to see sample questions. All the following, that is the sample question. Let us sample those slides. Just move next, the next, press next, so that they be recorded in the video. Okay, those are the questions. You can get the video and be able to do them. Just press next, 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 and we just record the questions. Those ones, then up to the last part. Just press next, 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 next. They will be recorded and someone can view them as he or she stops the video. Okay, so allow me say that we are going to, it's okay, they are over. Allow me say that we have ended this topic, which is thermochemistry. Tomorrow we shall look at a very simple and interesting segment. I've been Saul Chiamanywa, or you can call me Saul Abooki, your teacher today of chemistry. Let us meet tomorrow, same time.